introduce our second speaker, who's going to be talking about FairBranch, mitigating bias transfer in fair multi-task learning. Over to you, sir.
Thank you. I would like to thank the chair and of course IEEE, WCCI and IJCNN for organizing this gala event, right? And inviting me or giving me this opportunity to present our work here. My name is Arjun. I am still pursuing my PhD in the final years of my PhD, doing it from Freie University Berlin. And I'm also working as a researcher at Research Institute of Cyber Defense at the University of Bundeswehr, Munich. This is a joint work with my colleagues Christos and Simeon from CERT, Thessaloniki, Greece, and my supervisor, Professor Irini Dulce. And this work is funded by European Horizon Project NAMO. So this is going to be the brief outline of what I'm going to talk today about. And I will start with first of all finding the motivation. What was the motivation behind this? As it is already evident from the title itself, instead of the traditional single task learning situation or scenario, where you need to actually predict given a or learn a supervised task, a single supervised learning task. Instead of that, we are going to talk about mostly learning multiple supervised tasks together concurrently. And this is traditionally done by sharing a representation space and concurrently updating the representation space, shared representation space from the different supervised tasks. Well, out of the many advantages that this sort of learning setup has, one of the key advantages is it improves, or it has been shown to improve generalization across different tasks. So that means learning more tasks together helps each other in learning each and every of them. But there can be also problem of overgeneralization. You cannot update everything together. So which task to update together, how to group them together is actually a challenging task. Talking about the challenge, let us first go through when something can be good to train together and when things can go wrong. With this hypothetical example, where given this hypothetical loss surface of these assumably two parameters which are shared between this task 1 and task 2, which you see with red arrow and blue arrow. And they are in their gradient update or their gradient directions in the loss surface are sort of moving together. That means they have a very common goal of agenda of going towards very similar, let's say, minima. And in this case, of course, they are going to boost each other. They are going to help each other in learning better. However, this cannot be the scenario always, right? There can be, for example, say in this another example, two tasks having their local minima in completely opposite direction. That means what they will do now, they will try to actually pull each other into opposite directions. And what it will result is that when they will be trying to update the shared parameter space, they will cancel out each other's effect. So maybe the model will not go anywhere or will be stuck in a very bad space, and or will go towards if it is a weighted average, trying to give weight to one task more than the other, then it will pull the other task towards that. So why this is problematic? To understand that, first we need to know how we can actually judge how good our MTL is. So out of the several ways to measure it, one of the key ways to do it is by understanding what is the advantage that I'm getting of learning a task with an MTL. And how we can do that? By comparing it with learning the task in isolation, that is with an STL, single task learning. And measuring the difference between the performance of the MTL with that of an STL and checking whether if the difference is at least 0 or in the positive side. That means the MTL has an advantage or at least do not have any disadvantage of learning the task in the shared space compared to learning the task in isolation. However, like this does not happen always, right? Like here in this example, you can see like there are a lot of green triangles, but like there are also a bunch of red triangles. These red triangles indicate like negative learning, or let's say like the degradation of the performance on a task when it is learned in the MTL setup. And this problem or this phenomenon is coined in the literature as the negative transfer problem. It has been identified in the related research that one of the key root causes of such negative transfer problem comes from the conflict of accuracy or the conflict of gradients update. And here in this example also you can see that like these two particular competitors that we have, Recon and TC-Grad, they both directly tackle the conflicting gradient problem on the parameter space. And they seem to have like an edge over all the other competitors. Okay, so now that we are like very much familiar like with what an MTL is, what can be a problem in MTL, traditional one, we have to move to the other part, right? Like we also have the fairness part involved in it. So what is a fairness aware MTL? Basically, like what are the challenges? It's almost same as like traditional single task learning with an additional challenge that like now here you have to adhere like this sort of like with certain measures. For example, say this is like a fairness violation measure given by any condition C. This C condition can be anything. For example, say like whether false positives of between male and females should be equal, or like whether like true positives should be equal, something like that. And based on that condition, the definition of that like the fairness notion will change. But anyways, like the main agenda is basically like to have sort of like equality in predictions between different demographic groups and across all the different tasks. And how it is done? Traditionally, it is done by like adding like another loss for each and every task on top of the accuracy loss. So now we'll have to also optimize for a fairness loss in order to make the model also learn fair predictions in all of the tasks, right? Now what's the problem? More loss means more chances of conflict, right? And one such conflict can be like between fairness gradients of different tasks. What does it mean? That like now, similar to the negative transfer or similar to the like accuracy gradient conflict problem, here fairness gradient update when done on the shared representation space, having let's say like different goals of fairness among the different tasks, will try to pull each other in different directions, making the model like learn maybe like nothing fair or even worse, like degrading the fairness performance. And we have observed that state-of-the-art MTL models have shown this kind of like conflict in fairness gradients in real-world data sets. And what does it like eventually matters? Where it matters? So similar to accuracy, first we have to actually also evaluate like how we can like evaluate the fairness performance of any MTL. Similarly, like we want to actually also judge it comparing with the performance of any STL, like learning the model in a fair single task learning, and trying to check like whether this fair single task learner is better than the MTL, or the MTL has an edge over it. And if the MTL is having like a like let's say like a more violation of fairness compared to the STL, then we call it like a gain in discrimination. So what we don't want, like we don't want to, like we wanted previously like to gain the knowledge, basically like accuracy knowledge, but we don't want to gain like the knowledge of discrimination. That is, like, we don't want to have a positive discrimination gain. That means we don't want to have the triangles in the positive side. These are the red triangles now. So ideal scenario is like, of course, like non-positive. That means at least like the MTL model mimics the performance of the STL model or learning it in isolation, or even better set, like the main purpose of learning MTL. And this is our hypothesis, like similar to like the negative transfer problem, like the root cause of this sort of like gaining discrimination, which we coin as bias transfer problem, is coming from the conflict of fairness gradients in the shared representation space. And here also you can see that like even fair MTLs, that means like MTLs that have some sort of like fairness aware learning incorporated within the model, they still show this sort of like discrimination gain or bias transfer problem with the rectangles in this again like the real world example. Coming to our solution, FairBranch. So what we wanted, like the properties or the characteristics that we wanted to maintain for FairBranch is like, first of all, like we didn't want it like negative transfer, so we wanted to eliminate like accuracy conflicts. We didn't want like we wanted like the model to behave more fairly. Like that means like we didn't want discrimination gain from on like any of the tasks. So that means we wanted to also tackle fairness conflicts. And in the beginning I mentioned that like you cannot just simply learn everything together. So we have to also figure out like which task is beneficial, or like how we can actually segregate this learning of like non-beneficial tasks and only keep the beneficial tasks together. And this will prevent us from overgeneralization. That means we don't want to generalize everything within the shared space. And our proposed model actually tackles all of these three, or ticks marks all these three characteristics. How we do it? First of all, like we address the negative transfer problem by grouping, by finding tasks which have a similarity in the parameter space, which actually like updating the parameter space similarly. So we do this using like a parameter similarity matrix, which is based on center kernel alignment. I will not go into the details of center kernel alignment, but like in the questions, like question answer session, like if you want, I can explain. Then we also wanted to like address like overgeneralization. That means like whichever groups that we figured out like using the task similarity, now we want to actually create a different, let's say like branch. So we will not exactly learn a different model, but like we will segregate more. That means they will share less number of parameters together. So more closer they are towards the classification layer, the more segregation they will have with unsimilar tasks or dissimilar tasks. And we also correct like the fairness conflicting fairness gradient problem, and this we do by projecting the gradients into each other's normal plane which are conflicting. And this is like a inspiration that we took like from the PC grad mechanism proposed in the literature. And this is like the actual thing that happens, or like a very high level depiction of like the actual thing that happens. Like we try to steer the fairness gradient towards a direction of each and every task where they are sort of like still learning similar, like they are not very deviated very much from their own goal, but still like they also have like a common joint goal. Experiments. Okay, so we did like okay. So on our experiments on real world data sets, like we first of all did like on tabular data, like experiments on tabular data, and here we figured out that like our model outperforms like all the state-of-the-art MTLs competitors, effectively tackling both negative transfer and bias transfer problem. And among the competitors, we also saw that like the models that actually tackles this negative transfer problem on the parameter space are outperforming all the other like competitors. So this was a good decision to tackle the negative transfer problem and this conflicting gradient problem on the parameter space itself. Similar type of observations that we have also noticed like in the visual, in our experiments on the visual data set as well. And here like also we stressed the MTL really with a large number of tasks. Here we saw that like even though like we tackled negative transfer problem very well, but like somehow like we still had some bias transfers, even though less than the competitors, but like we still had some red triangles. On an average, of course, like we did like outperform all the competitors in most of the evaluations that we have seen, and this proves like how beneficial our or how advantageous our proposed method is compared on top of the competitors. But still, like we saw that like in the visual data sets, like we had some sort of like bias transfer. Still, like we were not able to mitigate completely everything together. Because like there were certain tasks that we figured out, which although like dwell with all the other tasks well in terms of accuracy, that means like they were advantageous to train with any other task on terms of accuracy. But like in terms of fairness, they were creating a lot of problems. So it confused the model or like made the model sort of like in a very confusing state to judge like whether to keep these tasks in a group or whether to learn them in like isolation. And this is a problem that we need to like still address in future. So concluding, FairBranch, like our proposed method, tackles negative transfer and bias transfer problem better than the competitors. We outperform like also on average performance, and tackling negative transfer problem on the parameter space is advantageous. And learning fair multitask, learning a fair multitask learner is challenging due to this complex decision making that requires where certain tasks can contribute positively to like knowledge transfer, but like while hindering fairness knowledge transfer or discrimination. Thank you everyone, and we can now move over.
Okay, it's 9:09. We've got time for one question. One question. It's got to be quick.
Sorry, it's I need a pre-question first and then a question. I'm a bit ignorant on this subject, so I was wondering how you set up these tasks, because I mean, let's get the example you gave of male and female. Let's suppose that you want to classify the life or regress the life expectation of male and female based on images and so any other parameters. So your task would be the life expectation of one group and the other group, and you give it separately and predict separately, and then you give it together and predict together. How?
Okay, so like this is like another different line of work what you talked about. This is actually like learning fairness using multitask learner, and this is not like we are doing. We are actually doing multitask learning and learning every task fairly. That means like for every prediction task, for example, say like in this image, if there is a QR code, or okay, this is a bad example. Let's say given a face, like if the person is smiling or not, like the model should be able to detect equally well for both males and females. So this is like one task.
So, and then my question on the actual question on the experimentation and so on and setup is that because you are working with neural networks, and then you have I'm supposing that this is for neural network
yes.
only, but then you have your data that is, I mean, at first you don't know how the data is distributed, if it's more male, more female, or whatever you want to classify. And I believe that if you train it as a multitask and a single task, you increase the one level of degree for the model to bias the outcome. Because if your data has more females than male, then if you train it single, it should be different and better than training it together. But it's not because of the task, it's just because the data is already messed up. So how do you cope with that?
This is actually like in any real world data set, this is a problem. This will be a problem. The deeper you go into like the distribution or cardinality or groups, the more like sort of like imbalance we will have. Come on, like we live in an imbalanced world. There will never be a balanced data in the real world scenario. So you cannot like let's say like assume like you will have a balanced data. And in order to actually tackle that, but like whether a imbalance in the data actually matters or not, that can be just only like using some evaluation, right? Like it doesn't matter like whether the like the data set has some sort of like imbalance. What it matters is that like if the model is learning or like mimicking that imbalance, like so the model should not be actually like in its knowledge mimic that sort of imbalance. And in order to ensure that you let's say like regularize the model or you train the model with like some fairness laws or like restrict the model with some constraints, and there are many different ways to do that, but like yeah.
Okay, I'm going to stop it now, only because we're 2 minutes over and we've got a lot of papers to get through. Well, thank you very, very much.
Thank you.